In this use case, we'll create a command line application. What we want to do is to read a bunch of subtitle files and then clean up those files. And by clean up, I mean removing the redundant parts of those files, such as timestamps and section numbers and certain meta tags. And after cleaning up the files, we'll save them to a separate distribution folder or a dist folder as new files. I'm planning to use those cleaned up files as transcripts for the video lessons of this course, so this is not just a dummy application, it's something practical that at least I'll be needing and using. So let's begin, shall we? Here's how our typical transcript file looks like, and here is how the end result will look like when we clean up the transcript file. So in my project root, there is a data folder that I have 30 or so of those subtitle files that need cleaning up. And again, under the project root, I have created a dist folder where we'll eventually save the cleaned up transcript files. This run function will be our entry point. So let's outline what we want to do inside that run function. We want to get a list of transcript files that we are going to process. Then we'll initialize a buffer or a cache that contains the names of those files, and we'll gradually consume that buffer until all the files are processed and there's nothing left in the buffer. In essence, that's what our entire code will do, so we are just going to fill in the blanks. Also, since getting the files is more like an I/O operation, I'll require it from an I/O module that we are going to create shortly. And we'll also move these cache-related init and consume functions to their own cache module and require it from there. So let's first create this getTranscriptFiles method, as it is relatively simpler to implement. First, we'll export this function like this, and then we'll write the body of the function. So since this is an I/O-related module, I'll probably have to resolve paths, and for that I'll require the join method of this path node module, which is a standard library function. And also we'll be reading the subtitle files, and we are also going to create and write cleaned up transcript files, and we'll need to list the contents of our data folder to get a list of the subtitle files. So for that, I'll add read file, write file, and read dir methods of the fs or file system node module. Then I'll define my data and dist folders as constant paths, and I'll also define these two extensions as well. So I'll read from the VTT subtitle files and eventually save the cleaned up transcript files with Markdown or MD extension. Since getTranscriptFiles is an async function, we'll have to return a promise from it, and inside that promise we are going to read the contents of our data directory, and if we cannot read the data directory for some reason, we'll reject the promise, and if everything is fine and there is no error, we'll resolve the promise with the list of files that we received. So let's try this first. I'll comment out the rest of the code that we haven't written yet. And once we run the code, we get a list of files with VTT extensions. So it looks good mostly, but with just one problem. We have this .keep file that I don't want to process because it's not a subtitle file. So how do I filter it out? Well, since items is an array, we can use the array prototypes filter method to filter out the things that we don't want out of that array. So I don't want this .keep file. And since I am on a Mac system, sometimes my operating system can create these ds_store files in my folders, and I don't want to include them in my file list as well, so I'll filter them out too. And when we rerun the code, we'll see that the .keep file is not included in our list anymore, so we are good. That done, let's also create our cache module. We'll need an init method to initialize our cache, and we'll need a consume method that will gradually process what's inside the cache until we exhaust everything that we have in the cache. I'll create an internal store array, and I'll also create this empty function, which is a helper function that checks the length of the array and returns true if the store is indeed empty and false otherwise. And if our internal store is empty, we'll immediately return a resolved promise, and that promise will indicate that whatever we have in the store has been consumed successfully. Otherwise, we'll create a recursive promise chain as follows. First, we'll create a promise that resolves with a subset of our batch, which is this getNextBatch function's return value, and then we'll chain that promise to this consume method itself to process the next batch of items on the next tick on a separate stack frame. So as long as we have stuff in the store, we'll chain consume, and since consume returns a promise, we'll wait for its eventual fulfillment value, and once the store is empty, we'll return a resolved promise, which will be our final resolution value that will also end the chain of promises that we created. So if this is the first time you are seeing a recursive promise chain like this, it might take a while to wrap your head around, so take your time and feel free to pause this video and think about what this code is doing. In the getNextBatch method, I want to return a subset of items, and to determine the length of that subset, I thought the amount of items that we want to process in parallel need to be proportional to the number of CPU cores that we have. So roughly, I need to split my workload across the number of CPUs that I have evenly. So I'll get the number of CPUs by doing an OS CPUs.length, and then I'll splice my store array like this, and that code looks a bit funny, but what it essentially does is it will return the last CPU count items from the array, and then it will truncate the array. So if we initially have 25 items in the array, and we have 4 CPU cores, this function will return the last 4 items in the array, and also it will reduce the size of the array from 25 to 21. And then when we call the getNextBatch again, it will give another 4 items, and the size of the array will be reduced down to 17, and so on. So let's log the length of the store here, and we also need to fill in this init method. The init method was taking a list of files, so for each file that this init function receives, we are going to push that file name to the store, and now when we run the code, we can see that the consume is processing the store 4 by 4, which is the number of CPU cores that I have, so it looks like that part of the code is working. So I'll extract this dummy promise into a cleanup files method, which will take an array of files and return a resolved promise, and when we run the code, it will work just as it did before. And I also want to move this cleanup files to io.js, since we'll likely be reading files and writing to files in that cleanup files function. So that function is a better fit for the IO module, and then we'll start writing the body of the function. So to utilize all the CPU cores that we have, we'll transform these files in parallel, and for that we'll use promise.all. And since promise.all accepts an array of promises, we'll map this files collection that we have into an array of promises like this. For now, I'll just log the file and simply resolve the promise and test if the code works, and it looks like it's working. And then for each file, I'll read the file in the data directory and then do a cleanup transformation on the file in this handle file cleanup method. I'll pass the resolve function as an argument to handle file cleanup so that I can execute it from within that function as well. And when I test it, it will run identical to what we had before, nothing surprising. So now I'll just do a tiny change, and instead of passing file as a parameter, I'll pass it as a destructured object like this. And again, it's just syntactic sugar, and nothing will change in the code execution. Now I'll do something interesting, and I'll increase the order of this handle file cleanup function. So instead of a plain function, it will be a function that returns a function, also known as a higher order function. For that, I'll take this error and data parameters here and move them here. And if you think about it, nothing has changed in the code again, and when we execute the code, we'll still get the same output, but this way we have separated our concerns just a little bit better. Now let's fill in this handler, and if there is an error while reading the file, we'll just reject and return like this. And if we can read the file contents, we'll write the file without modifying it at all to the distribution directory. The only thing that we are going to change will be changing the file extension from VTT to Markdown. Again, if there is an error, we are going to reject the promise. And if there is no error, we are going to resolve with a success message. And when we run the code, we'll see that our dist folder is populated as we expected. Now let's say we want to change this data instead of directly writing it. So we are going to pass it through a clean VTT content function that we'll create shortly. And since string cleanup is more of a formatting thing, I'm going to create the code inside a format module, and I'm going to require it here like this. And for now, I'll just create an identity transformation as in here. Or actually, let's convert the content to uppercase just for the sake of testing it to see a change in the output. And then we'll run the code. And when we look into the dist folder, we'll see that the output text is all uppercase. So our transformer is working. We just need to define what to replace and how to replace it, which we'll do next. For that, I'll create a bunch of constants first. This by new line is a regular expression that we will use to split the text into an array of lines. These two tag regular expressions are to match and remove the VTT author tags that you see here. This VTT arrow is the timestamp arrow that I want to filter out the entire line if I see that arrow. And this web VTT is the header line that I want to get rid of as well. So when we split the data by this new line expression, we get an array that we can work on. Then we first filter out the blank lines by this expression. And after that, we exclude the lines that have VTT arrows in them, followed by excluding the VTT header as well. Then we remove any lines that only contain a number but nothing else. And after that, we join the array into a single string by adding a new line at the end of each entry. And finally, we remove the beginning and ending author tags from the text and return it as our outcome. And that outcome will eventually be written into the transcript markdown file. Wow, that was a mouthful. So let's test if it works. But before that, I want to rename these variables because I prefer using camel case in regular expressions, but this is just a rename, so it won't impact how the code works anyway. So when we run the code and check the output, I see that all the contents have been cleaned up and the resultant transcript markdown files are reasonably easy to follow, so they are ready to be added to those lessons pages as transcripts. And this code actually saved me hours of frustration and hours of manual editing time, so I'm really happy with this outcome. And as the saying goes, don't do anything yourself when a machine can do it for you.